Alright, in this next video we're going to look at the first question on the worksheet that says find the center of mass for a thin metal rod of length L where, and in part A it says the density is uniform. Okay, so if the density is uniform, then we're really just saying that our density function rho of x is just constant, so I'll call that constant k. And a little note here that the center of mass, in the case when you have uniform density, is also referred to as the centroid of the solid. It's also referred to as the geometric center. Okay, so you don't need calculus to solve this question. If it has uniform density, the balance point for the rod should just be right in the middle. Okay, but nonetheless, we'll go ahead and do the calculations using what we derived in the intro video. So recall what we referred to as the total moment of the rod. This would be the integral of x times our density function. So this is just saying the position along the rod x relative to the reference point x equals 0 times the density at that point. Okay, and then we sum those up to get the total moment. And then the mass, we're just integrating the density function. And we've seen that kind of calculation quite a bit now in this chapter. To find the center of mass, then we just took the ratio of the moment to the mass. Alright, so now let's go ahead and do those calculations for a constant density function. Also notice that they don't specify the interval, but since the rod has length L, we'll just, for simplicity, label the interval as 0 to L. And so our mass then would just be the integral of this constant k from 0 to L. So that would just be, well, the density times the length, right? Which again, you don't really need calculus to answer that, but that would be our mass. The moment, this would be the integral of x times the density, which is k, from 0 to L. That's going to give you kx squared over 2, and evaluate, you'll get kl squared over 2. And the center of mass then would be the ratio of the moment to the mass, and that's going to give us, well, as we expected, L over 2. Okay, so it's that geometric center. Okay, and remember, one way to think about the center of mass is just thinking about the point at which the rod would balance. Another way to think about it, though, right, is in terms of this rotational tendency that this rod would exhibit relative to this reference point 0. And what the center of mass is saying is that if I were to concentrate all the mass at this midpoint, okay, then that point mass would exhibit the same rotational tendency as the entire rod. Alright, so now let's check out part B. Here we're looking at the density function being equal to 0 at one end of the rod and is equal to A at the other end of the rod, and we're also told that it increases linearly as we move along the rod. Okay, so if it's linear and we have a value of 0 at x equals 0 and a value of a at x equals L, the slope then must be a over L, and since we're 0 at 0, the intercept there would be 0, so there is your density function, a over L times x. Alright, so now go ahead and do the calculations. Again, pretty straightforward, so I've just done them ahead of time. For the mass, we're just integrating a over Lx, the density function, and that's going to give you just Al over 2. For the moment, we're going to integrate, well, x times the density function, which simplifies to a over Lx squared. Integrate that, it's going to give you Al squared over 3. Alright, and then for the center of mass, we're just going to divide the moment divided by the mass, and we wind up getting 2/3 L. Okay, now what's interesting about this is that you don't see the value of A in this expression, right? It's just saying go 2/3 along the way, and that point right there is going to be your center of mass, totally independent of this value of A. Now it does make sense that it would be towards the higher end, right? Because we are more dense towards the higher end. So going back to that seesaw example we looked at in the intro video, it would make sense, right, that we would want to have the higher density stuff closer to this balance point than the low density stuff. But again, nonetheless, it is interesting that this answer is totally independent of that value of A. All right, and then let's go ahead now and look at 15. So we're now looking at, sorry, not 15, part C, sorry, it's getting late. The rod lies along the interval from 0 to L, and the density function is given by the expression 10 over 1 plus x squared. What happens to the center of mass as L approaches infinity? Okay, well, let's first just think about what's going on with the density function. If x is 0, I'm going to get a density of 10. And notice as I let x increase, my density is going to decrease, kind of like this. And then we're going to actually approach a density of 0 as we let x become infinitely large. Okay, so we're becoming less dense as we move along the rod with a maximum density at 0 with a density value of 10. And so now let's go ahead and do the calculations. Again, I've done these ahead of time. So for the mass, we're just integrating the density. That's going to give you an arctan and evaluate there. Remember, arctan of 0 is 0, so you get 10 times the arctan of L. Now for the total moment, well, now you're going to do x times the density, so that'd be 10x over 1 plus x squared. That's a logarithmic integral, and so you could do it by a substitution or just basically a chain rule in reverse with the logarithm there, and you wind up getting 5 times the log of 1 plus L squared. And the center of mass then is just the ratio of those two. So that simplifies to the log of 1 plus L squared divided by 2 times the arctan of L. And so now, to address this question, what happens to our center of mass x bar as we let the length of the rod approach infinity? Well, I claim that it approaches infinity as well. And to see why, well, as we let L get big, the log will approach infinity, whereas the arctan in the denominator is going to approach pi over 2, and we're doubling that. So this denominator is going to approach pi. So this entire ratio then would approach infinity as we let the length of the rod approach infinity. Okay, so yes, the density does decay and it does approach 0. So it's at least feasible to think that maybe that center of mass would kind of converge to some finite point, but the thing that's going on here is that our density just doesn't decay fast enough to actually have this center of mass converge. Okay, it's still going to get carried away to infinity. All right, well, that does it for this problem. See you in the next one.